This recording will help you write Lewis structures and basically go through all the things I could possibly ask you about Lewis structures of a molecule. So the first thing we can see is that I want you to draw the Lewis structure for CO3 negative 2. So I'm going to just draw this down here. So first thing I need to know is in CO3 negative 2 is how many electrons are available um, to make bonds. And so how many valence electrons are available in this compound. So I just look at the individual elements, and I know that carbon is in group 14, which has 4 electrons in its outer shell, and oxygen is in group 16, which has 6 electrons in the outer shell, but there are 3 oxygens. Plus, I see that I have a -1, a -2 charge, and so that means I've gained 2 electrons into this molecule from somewhere. So if I add all this up, I have 18 plus 2, which is 20, plus 4. So I have a total of 24 valence electrons to work with. So I'm going to then just connect my central atom. My central atom will be the one that you have a single one of, or the most lowest electronegative element in your compound. And I'm going to hook the 3 O's to it. So I see that in this process, whenever you hook the oxygens to the carbon or whatever element to the central atom, that each one of those bonds represent 2 electrons. And so since this represents 2 electrons right here, I need to subtract those 2 electrons from the bank of my available electrons. And so I know that I've just used up 2, 4, 6. So I've used up 2, 4, 6 electrons. And so that equals a total of 18 remaining. And so then I just double check and see how much do I need. Well, each one of these elements, there's not any that have an exception, like hydrogen will take 2, and beryllium is okay with 4, and boron is okay with 6. These guys are all requiring a stable octet. So I noticed that carbon has 6 electrons attached to it because of the bonds, so it requires 2 more. Then the ones on the end have 2 electrons in the bond, so they need another requirement of 6. So if I do the math on this, I can see that I require a total of 20 electrons, but I only have 18 available to me because I have 6 plus 6 plus 6 plus 2 is 20, but I only have 18 available. So what we do is what I kind of call this is a 2-for-1 coupon. So I'm going to come in and make a double bond on one of these carbons. So I'm just going to start over here. And I'm going to see that when I do that, I use up an additional 2 electrons. So I can't forget to subtract those. But now I can redo my math. So how many does carbon need now? Well, I have a total of 4 bonds. And so when I look at my 4 bonds, then I know that I'm fine on that. So I have a total of 8 electrons. But then this oxygen over here now has 2 bonds. So I have 1, 2 bonds, so 2, 4. I just need 4 more electrons. So just checking my math here, I need now 16, and I have 16. So I'm good to go. That means I can take my little numbers out of the way and actually put the lone pairs in to represent those numbers. And so the same thing here. I'm going to remove the 6, and I'm going to remove this 6 and put in my electrons. Now, this is a compound that has a charge, and so I do need to go ahead and put this into brackets and place a -2 charge on the outside of that bracket to represent that it is a polyatomic ion. So I've done step 1. Step 1 says check, draw the Lewis structure, and I've done that. And when I said check, let's just double check. I know that I had 24 electrons available to me. And how many valence electrons did I put on? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So it's kind of like a play on the commercial, but that's kind of a discount double check to make sure that what I put on is equal to what I had in my bank. So now determine the bond type. So what I want to look at is what is the bond type. What I mean by bond is more polarity. between the C and the O. So when I look on the periodic table, that carbon and oxygen are quite a ways away from each other when I look at electronegativity. So I can pretty much predict that this is going to be a polar bond. So the bond type between the carbon and the oxygen here is going to be a polar bond because of the higher electronegativity difference, where the oxygen will have a partial negative and the carbon will have a partial positive charge. So then the next thing I want to look at is determine the shape and the bond angle. And so I just need to make sure that I understand that, I'll go ahead and take this off here, that these bonds are actually the first bond that occurs are called sigma bonds. So those are little sigma bonds. So they're my sigma. And that this double bond here is called a pi bond. And I actually don't count that. I don't count that when I'm looking at shape or when I look on the VSEPR chart. So when we take a look at the VSEPR chart, I can see that when I looked at the CO around the C, that it had 3 sigma bonds connecting those oxygens. So I have 3 sigma bonds. I didn't have any lone pairs. So I can see that the shape is trigonal planar with a 120 degree for the bond angle. So that would be the answer for this question on determine the shape. So I know, again, we saw our Lewis structure, our bond type, that it was a polar covalent bond, and the shape was trigonal planar with a 120 degree bond angle. And so the next question here is, what is the hybridization? Well, I have a little trick for hybridization. And basically what I do for hybridization is I know that my choices for hybridization is that I can have an S, I have P's orbitals involved in my hybridizations, and I can have some D orbitals involved in the hybridization. And so what I do is I take a look at just the sigma bonds and the lone pairs. So all my sigmas and my lone pairs need to add up to the number of letters in my hybridization. So kind of just cleaning up my molecule here a little bit. What do I have around carbon? Well, I have 1, 2, 3 sigma bonds. And so how do I count that? Well, it's like this is 1, 2, 3 letters. And so since I have 3 letters, I need an sp2 hybridization. So that's the kind of hybridization that is taking place around carbon. So I'm representing that's spp, which we write down as sp2. So the answer for the hybridization question then is sp2. And that really the reason for that is it has to remove that p orbital to make that pi bond. And so that's why it's not sp3 hybridization. So the next question is the molecule polar or nonpolar? Well, I know that I have the first criteria. The first criteria is I got to have a polar bond. So the bond between carbon and oxygen is polar. But my second criteria is it needs to be asymmetrical. Well, there are no lone pairs. There's nothing sitting out on carbon here. There's no lone pairs that are going to cause it to skew my molecule. Because of that, because it is in that planar, it is symmetrical. And whenever you have a symmetrical, even though I know that oxygen's slightly negative, my carbon is positive, it is rearranged in such a way, so if I actually were to draw this correctly in the way it's shaped, it would look like this. And because of that, this little plus, minus, minus, minus is in a plane. It's symmetrical. That makes it nonpolar. You have to have pretty much a lone pair that's going to push it down, going to make it asymmetrical to make it a polar molecule. So this is a nonpolar molecule for that question. So this particular molecule is nonpolar. So then the last question, draw resonance structures, if there are any, for this compound. And so I'm going to just go to a clean page. And we, again, remember that we have our oxygen. We drew originally our double bond down here. with our 2 lone pairs around oxygen. This one had 6 lone pairs, and this one also, or I'm sorry, 6 lone electrons, 3 lone pairs. And so what's another way I could draw that? Well, are we sure that's where the double bond is, or can it be on this oxygen? And so we take a look and just kind of move it around. So I have another possibility also. So I can move the double bond to the top. And so those are actually 3 possible resonance structures for the CO3. And again, I need to remember to put them all in their brackets. So, and I didn't have a lot of room on that one. I'm trying to make it neat, but that's not happening. Okay, so those are my resonance structures. So you just draw all possibles. You just move the double bond around. And because of that, that's why it would show an equal bond length, because it's really an average. This is not really a double bond, but there's kind of an average of bonds among them. Well, the last question, if we go back to it, just ask you to calculate the formal charge for this compound and just see if it really makes sense. So I'm just going to do that right here. So for formal charge, what we're going to do is I'm going to take a look at just this first resonance structure, and we're going to calculate the formal charge for each element. So to calculate the formal charge, there's a more formal formula, but I think this one makes a lot of sense, and it works. And so the formal charge is equal to the valence electrons. So I know it's equaling to the valence electrons normally of the element minus the lone electrons, not the lone pairs, but the actual lone electrons, plus how many bonds it has. The original formula is half the bonding electrons, but that's always going to be 2. So half of that would be 1. So the number of bonds works. So on formal charge, I'm going to do every element. So I'm going to look at, and I'm going to do the oxygen. I'm going to do the oxygen first. That oxygen that has the 3 lone pairs. And so to start off with, its formal charge, and this is bonded to the carbon here. So its valence electrons for oxygen is 6. Its number of lone electrons is also 6, and it has 1 bond. So when I take a look at that, that has a formal charge of -1. So I know that up here, this oxygen and this oxygen down here are both the same. It's going to have a formal charge of -1. So now what I want to do is look at the oxygen with the double bond. Well, what changes here is that I do still have a valence of 6 for oxygen, but in this case I only have 4 lone electrons, but I also have 2 bonds. And because of that, this actually has a formal charge of 0. So this particular, the double bonded oxygen, has a formal charge of 0. So then the last one I want to do is carbon. We can see that carbon had, it looked like this, and so carbon has 4 for its valence. It has no lone electrons, but it made 4 bonds, and so that also equals 0. So the overall, if I go back up here then, and I know carbon was also 0, that I can see that the overall formal charge for this compound, for this polyatomic ion, is -2. Well, that helps me a lot because in my question now, because I know I have 2 oxygens with a -1, and then I have 0 and 0, so the overall formal charge for the compound, for the formal charge, is a -2. Well, now if we answer the question, is this an appropriate compound, or is an appropriate diagram for structure for the carbonate ion? And it is, because first of all, we need to have elements, formal charges, the lower the better, plus it has to equal, if it's an ion, the formal charge has to equal the charge on the ion. So it does equal -2, and I have a -2 charge on my ion. So it is appropriate. So if we just kind of go back and we then kind of just glance again over this, we drew the resonance structures. We saw that there were 3. And then we assigned the formal charge to each atom, and we saw that, yes, this structure is likely because of the low formal charges of 0 and the fact that the overall formal charge for the ion is -2 and the charge is -2. So hopefully that helped you in drawing these structures.